what we're looking for is an amplifier. If we put it into a box like this, amplifier. Of course, differential amplifier. Differential amplifiers have two inputs, without exception. They are marked positive, they are marked negative, and they have usually one output or often two outputs. One is output, the other one is output bar, the negative of the output. They have two voltages there, V1, input voltage, this is an independent input voltage, input 1, and they have another input 2, V2, input number 2. They have a gain, A, which this gain is called differential gain. Sometimes it is denoted by a D, sub D, so we know it is a differential gain. So the amplifier has a symmetrical gain for both positive and negative inputs. So this output voltage is dependent on two incoming voltages by superposition. If you short circuit one voltage source to ground, the output voltage will be equal to AD, positive AD, multiplied by V1. Okay? This is with V2 grounded. Output with V2 grounded. Then, if you ground V1 and you apply a voltage to the V2, the output voltage will be equal to minus AD multiplied by V2 grounded, multiplied by V2. This is with V1 grounded. Okay, so it will invert incoming voltage V2 and the output, and it will non-invert the incoming voltage at the V1. If you apply simultaneously, what will happen? You will have VO by superposition, The output will be equal to AD times of V1 minus AD times of V2, which will add up to AD multiplied by V1 minus V2. This difference voltage between the two is called differential input voltage. Differential input voltage. Differential input voltage. Often it is called VD, which is V1 minus V2, the difference of the two. VD can be marked where it is on the diagram. This is the VD. As if you take the voltmeter, you put between positive and negative and you measure. That's called the differential input, because it will be the difference of the two voltages, V1 minus V2. So pretty straightforward. The important conclusion here is that the output voltage is independent of absolute size of V1 and the V2. Of course, up to some extent, it's independent. Doesn't matter what is V1, doesn't matter what is V2, it's the difference of the two. If you raise both of them simultaneously, but you keep the difference the same, it's the same as you keep both inputs low, but you keep the difference the same. For example, if you make, this is dry. If you make V1 equal to 6 volt, and you make V2 equal to 5 volt, with AD equal to, say, 10 times, then the output voltage is going to be equal to 10 times of the difference. 10 times of 6 minus 5, which is equal to 10 volt. 10 volt. But if you make V1 equal to 3 volt, and you make V2 equal to 2 volts, with AD equal to 10, still, the output voltage is going to be 10 times of 3 minus 2, which is equal to 10. Same as this one, as that. So the value of the 6 and the 5, that voltage, is rejected by that amplifier, provided the difference is kept constant. Now, why is this important? This is important in industry. Many medical instruments are really owing their operation to the differential amplifier. Here is the reason for it. If you have a heartbeat like that, and you want to monitor voltage close to the vicinity of heart, you have a plus and a minus VD, a differential voltage, which due to the heartbeats, it is about a couple of millivolts. It's created in the vicinity of heart. Actually, in few places, near heart, on the chest. So we want to magnify that signal because it's about 2 millivolts. We need considerable amount of gain to amplify. To amplify that, we will carry these signals with wires, but of course with special wires, to our differential amplifier. With a gain of 80. The positive, negative input of the differential amplifier. Now, this is the target where we want to amplify VD. So we would want to get VO AD times of the VD. In order to make sure that the amplification is good, we will use known as shielded wire. And ground the end of the wire. This is called shielded wire, which will minimize the influence of the pickup stray electric signal inducing voltage at that point, because these wires can be long, a few feet away from the target. So is this one. Specialized shielded wire here. Okay. Here is the ground, 0 volt ground. Okay. Now, the problem is that we are going to pick up a lot of signal at that vicinity, because our body is coupled from the air, known as space capacitance, with the hot wires that are running overhead. So a lot of voltage is induced at this point with respect to the ground. So this voltage is called common mode voltage. VCOM, known as the common mode voltage with respect to the ground. So what happens if you are taking the wrist, this is the wrist here, and you ground the wrist with a ground wire, a 0 volt ground. You get 0 volt here because it is at that node, at this node. You get a 0 there. But between that node and here, from here to here, you get this V common mode voltage, which you don't know even how to control it. It's in the environment. There is no way of getting rid of it. You cannot get rid of it. But what happens to this amplifier when it is differential? Check here. So we've got a voltage source in here, plus minus VD, another strenuous voltage here, VCOM, which is interfering voltage, between that vicinity and the ground. And let's see how the amplifier will respond. Now, if you short circuit this voltage source to the ground, the differential voltage will reach the input, the output voltage will be 80 times VD. So this is called the signal, the good signal. Signal amplified. VD is the signal. This is the signal. So you will get good amplification of that signal. But the second thing is, if you short circuit now VD, that voltage source, then VCOM will simultaneously applied to both positive and negative inputs. All right? So what will be the superposition of the VCOM? Well, let's use that principle of superposition. VCOM, because if this is VCOM, that's VCOM, you shorted, both are the common mode voltage. So it will be positive 80 times output, and then it will be negative 80 times output. The difference will be equal to 0. So you will get a clean output, only amplified signal appearing at the output. Okay? So this will be eliminated with a differential amplifier. There is no way that you can do it with a single amplifier. Check here. With a single amplifier, wipe this wire out completely. That's a single, say, non-inverting amplifier. So you're applying, you want to amplify VD, look what you're amplifying actually. The VCOM plus the VD multiplied by A. So the two will be superimposed on the top of each other. And usually, this common mode voltage shouldn't be underestimated. It could be as bad as about 2 volt. 2 volt, 100 millivolt, 200 millivolt, it's a big voltage. But the voltage VD, this one, so VCOM can be a pretty large voltage. This one is usually a couple of millivolts, 1 to 2 millivolts, that's it. So we're going to pick up just a spot, exactly voltage between 2 spots, close to each other. And we need these amplifiers. However, what happens in the actual amplifier? This would be the ideal amplifier. Ideal amplifier will reject VCOM. Okay? But what happens to the actual amplifier? When we build these amplifiers, unfortunately, the positive gain transferring to the output will not match 100% to the negative gain from there to there. So we will have dissimilar gains. It could be AD1 or AD plus, AD minus. For example, this could be AD plus can be 10 times amplifying that channel, but AD minus will be amplified maybe 9 times. Okay? Dissimilarity in the gains. It's possible because we need matching. An amplifier that has this property, which is 100% matching. So what will happen then at the output? Now check, if you apply VCOM at the input, you're going to see VCOM multiplied by AD1 or AD plus minus of AD minus by the discrepancy that exists between the two positive negative gains. So it will reflect at the output. For example, if AD positive is 10, AD negative, or the negative, is 9 or minus 9, then the difference between the two gains will be, it will be 10 times of VCOM minus 9 times of VCOM, which is 1 times of the common mode. So still, we see that the common mode voltage will be available at the output. The larger is this discrepancy, worse we are. The larger is asymmetry, the worse we are going to be. Because it will show more of this at the output. We don't want it. We won't see nothing of the VCOM here. Their ideal amplifier will reject VCOM. But if not, this is what you're going to see. VO is AD plus VCOM minus AD minus VCOM. So it will be equal to AD plus minus of AD minus times VCOM. So what is the total output in a practical amplifier? This is the practical amplifier. The total output, VO, tot, will be the sum of two things. It will be AD approximately, which is the average of times VD plus AD plus minus AD minus times VCOM. Here, AD is approximately, we need to define it, average of the two. Divide by 2. Because usually these two gains will be pretty close to each other. For example, if AD plus is 1000, AD minus can be 990. Okay, so discrepancy is only 10 times. 9,000, 1,000, and say 9,000. So the discrepancy is, 1,000 and 990. Discrepancy is 10. So here, as a result, if you take the average of two, average of 990 and 1,000, it's almost 1,000. Isn't that right? So we have one name for differential. What I wrote in here is just for mathematical reason, but actually there is just 80, one differential gain. So nobody says, hey, our amplifier has a differential gain for the positive this much, for the negative this much, right? There's another figure which will discriminate the quality of your amplifier. In a minute we will get there. So here comes the final thing. When we have a practical amplifier, if it had identical gains, positive, negative gains, you are absolutely in green because it will amplify the VD. It will reject the VCOM. The reason is by superposition, if you short that, the common mode input, known as common mode input, is a voltage which is simultaneously applied to the positive and the negative. So if the two were symmetrical, positive and negative were identical, nothing should come out of it. Gain 0 times VCOM. So this common mode voltage, which exists between heart and the wrist, where you're grounding the body, this common mode voltage would be rejected completely if the two were identical. Say 1,000 and minus 1,000. If you had that situation, that's perfect. You will not see VCOM. This one. The two will zero it. But if, the difference, yes, the difference would be almost average of the gains, which is one gain actually, AD, multiplying the difference. So you will see more of this rather than more of VCOM. Do you see that? There are two voltages playing, VD and the VCOM. You will see more of that one because this is almost like 995. It's the average of 1,000 and 990. It's 995 times the VD. But here, it will be 10 times of VCOM. So if VCOM happens to be a small voltage, a reasonable voltage, even a large voltage, reasonably large, like 10 times of the VD, this process will stop it, provided you can maintain complete symmetry within the amplifier. Now, this quantity has a name, difference of the two. It's called A, known as common mode voltage gain. Ideally, as small as possible. Ideally, should be as small as possible. So that ACOM is small. So what do we have then in general? This is your output. VO is equal to AD times VD plus ACOM times VCOM. VCOM is the stray signal, and VD is target signal. And this is the amplified output. Amplified output. Just in short, that's the introduction of differential amplifier with its two important features. Differential gain, common mode gain. Okay? Common mode, remember, ideally should be zero. Ideal of the common mode is zero. But you can't get it. Impossible to make this thing equal to zero. And this should be high. So they come up with a figure of merit for the differential amplifier. So figure of quality here. A figure of differential amplifier quality is CMRR, which is the ratio of AD divided by ACOM. So this is known as common mode rejection ratio, CMRR. CMRRs are usually so large, very high, because this number, it exists, but in comparison to AD, is very small, that it is expressed in terms of logarithm. So CMRR in dB is 20 logarithm of AD divided by ACOM. So manufacturer will give you CMRR. Manufacturer will give you that figure as how much it is. For example, in an amplifier, AD, say AD is 20,000, 60 dB, 60 decibel. This is the voltage gain. In dB is 60 decibel. That is 20 log of 80, known as AD in dB. AD in dB is equal to, just like power gain, but in the power we use 10, here we use 20 for the voltage gains. 20 log of AD, say 60 dB. Example. This is an example. Okay? And the CMRR is equal to, in dB, is equal to 80 decibel. 80 decibel. So let us look at the application. So we don't need this part, I can erase it. Here is the application. You've got VD, and then you have VCOM, and these are the two electrodes carrying to the amplifier. So as much as possible, one should shield it near the amplifier. So this is the amplifier input, positive, and this is the negative. So here, of course you have a positive supply, negative supply, grounds within your circuit and everything. This is near amplifier circuit. We'll build it there. So VCOM is equal to 2 volt peak to peak. 2 volt peak to peak. VD is a waveform, which is heartbeat basically. How does it go? Heartbeats, I think. Only 2 millivolt peak to peak. 2 millivolt peak to peak. This is the heartbeat, this is the VCOM. And this is our amplifier feature. CMRR is equal to 80 dB. AD is equal to 60 dB. So question is VO. What is VO and its component? What are the components of VO in terms of VCOM and VD? The interference, you want to calculate that. So how would we go about it? And you will see the influence of that CMRR. So this is how we will determine that. Output voltage is equal to AD multiplied by VD, second voltage, ACOM multiplied by VCOM. Two inputs, separate inputs. One is a bothersome common volts input. The other one is really the heartbeats. This guy here is extracted from X and X. X and X, as close as possible to the heart. Grounding the wrist, zeroing the body at that point minimizes. It really, really minimizes. But it does not eliminate VCOM. It will be there. So have you seen when they're taking tape from you, they say, don't move, when the tapes are attached or electrodes are attached? Because when you're moving, you pick up additional common mode voltage due to the static electricity. And the instruments can reject, but they reject only so much. I mean, if you start having friction, they can jam, saturate. The amplifiers can saturate. When they saturate, they won't function. So we want to determine that one. Here, we have to extract AD and the VCOM from the given information. Here, CMRR is equal to 20 log of AD over ACOM, which is equal to 20 log of AD minus 20 log of ACOM, common mode voltage gain. So this CMRR is 80, it's given. Given that CMRR is 80, AD is 60 dB. 60 dB. So we got 80 on this side, 60 for that one, minus 20 log of ACOM. You can work out what is the ACOM. 20 log of ACOM is equal to minus 20. So log of ACOM is equal to, that's 20, and this one 20 is equal to minus 1. Okay, so what is then inverse log? Is how much? Over minus 1? 0.1? It is 0.1. Inverse log of minus 1. Remember, negative numbers don't have log, but the log of numbers that are less than 1 is negative. Here. Log of A1 is that, so ACOM is inverse log of minus 1. COM is equal to inverse log of minus 1. So put it in the calculator. Here, 1, negative, take inverse log, equal 0.1. That's it. So conclusion is your ACOM is equal to 0.1. That's number 1. Number 2. What is then AD? 20 log of AD is equal to 60. So log of AD is equal to 3. What is inverse log of 3? Answer is 1,000. Answer is 1,000. Okay, so let us calculate the weight of these numbers that we have put in here. We conclude that this number, 1,000, that you see over there, is carrying here 2 millivolt peak to peak. Calculating it is magnifying the peak to peak of the signal by 1,000 times, and then VCOM, which is due to the asymmetry, defects of imperfections in the amplifier due to the usually asymmetry, or some other factors that we will look into it, is amplifying 0.1 times. Point 1 multiplied by 2 volt peak to peak. And this is equal to 0.2 volt peak to peak, while the other one is equal to 2 volt peak to peak. Okay. Do you see the improvement here? 2 volt peak to peak, that's what the heartbeat will be amplified, which we will see it on oscilloscope. The VCOM, which is a bigger voltage, like 2 volt in here, is rejected, but it will show itself by a value of 0.2 volt peak to peak. So this is what we are going to see finally at the output of that differential amplifier. So the output, typical output pattern is, you will see the heartbeats goes like this. Sorry. And so on. This will be about 2 volt peak to peak, while the superimposed common mode voltage will be that one. A little amplitude riding on the top of it. So the level of that one will be only effect of VCOM will be only 0.2 volt peak to peak, 10 times less than the signal. Okay? 10 times less than the signal. Signal to noise ratio, there is something that they call it, signal to noise ratio, voltage ratio, S over N, voltage ratio is equal to 10 into 1. 10 into 1. The power ratio, signal to noise power ratio, is always square of the voltage ratio. So S power to N power is equal to 100 to 1. This is the voltage ratio, this is the power ratio. Power ratio. It's 100 times. Again, usually signal to noise ratio often is expressed in terms of a dB. How many decibel that is. Can be converted. If this is a dB, it should be 10 log of 100. Well, 10 log of the 100 is 20. The voltage ratio is 20 log of 10. 20 log of 10 is also 100, you see? So it doesn't matter, it's voltage ratio or it is power ratio in terms of decibel. Once they become a dB, they're the same. They're exactly the same. So that's it. And you can see projection of actual heartbeats, which is here, is really effectively amplified with the gain, differential gain, AD, which is 1,000. This is your AD. While the other one, the common signal, which is the signal between here and the wrist. Wrist doesn't have any signal. Where you ground it, it's dead. There's no signal. It's 0 all the way. That is 0, but you can 0 here and 0 here as well. You see how many places you are going to place your earth. You can get close, you know, they don't go sometimes for the wrist, they go near heartbeat, but not too near because you can short circuit those signals as well. You weaken that signal as well. If you place the ground in here, you will weaken that one. So what we're going to do now, we're going to look into structure of the differential amplifier and see what makes it perfect, makes ACOM equal to 0, and what makes it better. And believe me or not, that ACOM has to do with the current sources. And in a minute you will see that. If that current source is closer to the ideal, yes. ACOM will be very, very small in comparison to 80. If that current source is less ideal and a larger internal resistance, it will ruin the ACOM. In a minute we will see that. So starting with the ideal amplifier. First of all, let's see what makes this difference. V1 minus V2, you know, like AD. What does make AD? Okay, so you're going to take a picture of that, like a reminder to you. It's a good idea. From here to the left. Okay, now let me erase that. From my own handouts in the Canvas, if I reach Canvas. But you know what? Don't want to waste my time. I'll just do it on the board. You have all of those in this handout. Lecture number 8. So let me write here. Lecture number 8. So here is how the differential amplifier evolves. Ideal. So we've got two amplifiers. Joined together like that. One has an input, we define it V2, and then the other one has second input, define it as V1. We take that point output, VO, automatically, and also here, we have a choice. If we could create ideal current, of course, ideal constant, I should emphasize, ideal constant current source, which would not change, going all the way to the most negative level. We need that in the circuits. Something here that provides constant current. Then for what I have shown in here, this will become the positive input. This will become the negative input. If that is the output. If this was the output, it will be the opposite. This will be the positive, this will be the negative input. So there are two resistors, RC, and the VCC, okay? One way of creating this current source is by the traditional method, which means, do you recall RE, emitter resistance in the transistor, going from emitter to ground? Here, you can make between X and X, you can put a resistor like RE the negative can be connected, this can be connected to minus VCC, and this voltage here will be approximately equal to minus 0.7 of a volt. This is V of E1, 2. Okay, let's see what that means. If you ground these two inputs, zero them, this is DC analysis. If you ground these two inputs, there is a current going to be in both transistors. So you've got to have a VBE in here, don't you? Base emitter voltage. Because VBE is 0.7 of a volt, this X is going to read minus 0.7 of a volt. Understood? Because both, that point is VBE. Two VBEs parallel to each other. That VBE is parallel with this VBE. Transistor 1, transistor 2. Q1 and Q2. Okay? So, what will be the current going in here through that resistor? I. It will be equal to VCC minus 0.7 divided by RE. For example, if you had 10 volt in here, negative 10, and you had a 10 kilo ohm resistor here, the voltage will be 10 minus of 0.7, then actually minus 0.7 minus of minus 10, that would be 9.3 volt, divided by 10K. 0.93 milliamp runs here. Runs in that resistor if you use a resistor. Okay? In other words, cut this, put it right there. Then that's how to calculate the, in this tail, they call it tail. In this tail, the value of the current. Now, see what else will happen. If this current was 1 milliamp, and this was 0, that was 0, VBE of that is equal to VBE of this, isn't that right? Because they are both same joint. And this is the same, you ground it. So both VBEs are the same, then guess what? Both ICs will be the same. IC of that will be IC of this, so is IE of 1 equal to IE of 2. As a result, this current will split 50-50 in this branch and that branch. Half of it will go here, the other half will go here. Does that make sense? Yes, have a question?
Just to clarify transistors, if there's no current going through the, if it's like, let's say we zero out like V1, V2, how is that current going through IE?
It can't, because this voltage sits lower. This is 0, that is a 0. But that point, it can be lower by 0.7 of a volt, because this is drawing the current. We have a source that gives way to the currents coming down. So these currents are flowing down. See, out of here, out of here. The two currents are equal because their VBEs are equal. As of now, when both are grounded, they are equal, equal, equal. So if the currents are equal, and this is a common source supplying that node, then obviously by symmetry, half of that will go here, the other half will go here. Okay, so the output voltage in here will be IC, and then voltage there would be VCC minus IC of that one times the RC. Same thing over here by symmetry. There will be the other half of the half of that current multiplied by RC. Two identical voltages will show here and there. Two identical voltages. Now imagine what will happen if one is kept at 0, the other one is changed a little bit. If you keep it at 0 and you change, an unbalance will be created in both transistors. VB of one will go up, VB of the other will decrease. See, this is an emitter follower. Remember, emitter followers have a gain of almost 1. So if you increase it by, say, 10 millivolt, this will rise, will try to rise, but because the two currents are equal, only half of that 10 millivolt will appear across this one. So if the currents are disturbed, bottom line, if you had a 1 milli here, and you had half milli, this will be the situation. With V1, this is with V1 equal to V2 equal to 0. But if you have V1 equal to say 10 millivolt, V2 equal to 0, the current in here will shoot up to 0.7 milliamp, will increase, base rising, collector current will increase. Collector current in here will decrease to 0.3 milliamp. So the amount of the increase in one current will be identical to amount of decrease in the collector of the second one. Why? Because the sum of the two must be kept constant. See the two currents coming out? This is forcing. This is forcing to keep both currents equal and opposite. In the balance, they are 50-50, but if they are disturbed with a signal, then if it increases, the other one will withdraw, will decrease, to keep the balance the same as 1 milliamp. Or, if this decreases, the voltage goes down, this will drop to 0.3 milliamp, that will rise to 0.7 of a milliamp. Again, the sum of the two currents will be same 1 milliamp. That's the only trick with the differential amplifier. Yes, sir?
Just to clarify, for the current equation, it's I equals VCC minus 0.7 over RE.
Here, this is V of RE. Agreed? V of the RE. That's the V of the RE, this one. Voltage drop on that resistor, because we have a tiny voltage there. If zeros, this will be minus 0.7. And you have a resistance that's a minus VCC, usually large voltage, minus 10. So actually a resistor is a way of creating a current source. Because what you have in here with that resistor, with this power supply, is actually a current source equal to going to minus VCC. It's a current source equal to VCC minus 0.7 over RE. So this is the I in parallel with RE between X and this X. So remember, a resistor in here is actually creation of a current source. Here. Imagine it is a resistor here. Do you remember a voltage source in series with a resistor can be converted to a current source in parallel with the same resistor? You guys remember that? That law? Voltage source, this is the voltage source. Of course, less by 0.7. So you divide that by the resistance, you create a current. But that current is parallel with the RE. So I cannot call this assembly an ideal current source, this whole thing. It's not, because you've got RE here, right? If you change that terminal voltage, then the current will change in this line because of this guy. If it wasn't, if this was infinity, what would be the case? Infinity. You change that, the current would stay constant because this would not cause any additional current. But you can't have infinite resistance in this path and yet have a current there. Isn't that right? You've got to have some kind of finite resistance to create that current. Only thing that can create that condition, infinite here, current source here, is a true, genuine, constant current source. The topics that we discussed before. So it is very important that we have an ideal current source in here. So the whole trend is to have a situation where the current in these two branches will counter each other. One increases by an amount, the other one will decrease by the same amount. one increases or decreases, the same thing opposite. Both remaining a constant. But if you put a resistor here, it will not happen. Because if I put a resistor there, grab these two, raise them up, bases will go high together, emitter voltage will go higher, again, less than 0.7 compared to what you're putting. The voltage in here will rise. As a result, if this was a resistor, the current limit will increase. So what will happen? Both inputs will go down in response to a common input. So we can see that how crucial it is to get an ideal current source in here, not just a primitive resistor. Because you change the voltage together, that's the VCOM, this voltage, VCOM. Then we don't want this currents to the sum of the two currents to change, because the sum has to be the same. So if you raise them together, emitter will rise. If you had a resistor here, of course, this current will rise, half and half will split into both resistors and both currents will drop. So you will get an output. In response to incoming input, you will see some kind of an output in here, which is no. We don't want it to see. We want it to be just a constant. Okay, so let's get to the material of it, the analysis of it. So this is your source. Primitive way of fabricating the differential amplifier is stick a resistor, and it will take care of it. And you can do the calculation very easily. Just stick the resistor, see what's, this is minus 0.7, see what that is, divide by it, you will get the IE, half and half. Then you can calculate VCE of each one, IC of each one, etc. DC analysis over. Very simple. But for what you have established now, what will be the AC model of this amplifier? Now we've got a different AC model. All the DCs are calculated very easily. Do you need me to calculate the DCs here? I can do it for you, just quickly. This is 10K. This is RE. Here is the I of RE. And minus VCC is minus 10 volt. This is plus 10 volt. These are, for example, 4K and 4K. So DC analysis. Okay. First, get IFRE. Assume V1 equal to V2 equal to 0. Grounded. Grounded. Both are grounded. IFRE is equal to minus 0.7. That's the voltage here. Right there, because VBEs are 0.7 each. 0.7 each one. They're identical. 0.7. Minus 0.7 minus of minus 10 over 10K. This is equal to 0.93 milliamp IE. IE1 is equal to IE2. Since betas are the same, and IS is the same, IS the saturation current. Two transistors are identical. Two transistors identical. Okay, this is a given. So IE1 is equal to IE2, therefore 2I of IE1 is equal to, or same as twice of IE2, is equal to 0.93 milliamp. Therefore, IE1 equal to IE2, approximately equal to IC1, approximately equal to IC2, is equal to 0.93 milliamp divided by 2. This will be 0.415 milliamp. 0.4 of a milliamp will be in each collector. 0.415 milliamp here, another 0.415 milliamp here. Of course, you will have IB for both of them. IB1, IB2. Because you can't have a current in a collector without having a base current. It's impossible. You've got collector current, you must have base current. Here, one important thing. Notice that already this amplifier is drawing current. You see that from that source? Which is a bad thing. Is there a solution that we could get zero input current? What would you use for BJT?
MOSFET.
That's it. Pair of MOSFETs. Identical MOSFETs will make this. Pair of identical JFETs will make this. BJTs will make that. Just, you have options, really. So guess what? Those that are utilizing MOSFETs, they are called FET operation amplifier, FET op-amps. They are different class. In the tendency there is to have zero current, like dead zero current. If that is important, yes, we've got solution. You build this, the two-stage with MOSFET, usually JFET. You build them. Then, what about the next? We don't really care. Usually we don't use JFETs. They don't have too much gain. BJTs are great with the voltage gain. So we get pair of JFETs building this, then the rest is NPNs all over for good amplification. It's only the first differential that you amplify important, because the later amplification does not change a common mode. This is what I'm saying. Imagine that you have a little discrepancy in here, AD. The AD, whatever it is, if there's a little mismatch, that mismatch will be amplified thousands of times, making it much, much worse. But of course, the same differential gain will also be amplified, post-amplified many, many times. The ratio will remain the same. So it doesn't matter how many stages you add in here. If you fail that symmetry in the first stage, you are stuck with it no matter what you do with your design, with the operation amplifier. This stage has to be the successful one. The most critical stage of the amplifier is that this one, the input. We've got to get good CMRR for this guy. We don't care about the rest. Okay, so we got that calculated. Now, what is VO? Here's the VO. VO is 10 volt minus 4K multiplied by 0.415 milliamp, and VOs are equal to approximately, what's that? 1.6, less than that, 10 minus 1.6 volt, approximately. That is 8.4 volt, approximately. Both will be the same. Here will be the same, there will be the same. And then you can calculate VCE. VCE will be this voltage, 8 minus 0.7, it will be like 9.1 of a volt. And then from there on you continue. So that's what the DC analysis is. It's just peanuts, it's a piece of cake over here. Once you know the other DC calculations, this one is just easy. So remember, whatever is current here is going to split half and half, here and there. From there on, it takes up. Now, the model, the small signal model. So here is the small signal model for the transistor. Just like before, you take the power sources, you short circuit the ground. Guess what you do with the current sources? Constant current sources. The same way that you short circuit the voltage source, you will open circuit the current source. Disappears. Nothing from here to if it was a current source. But if it had a dynamic resistance, RE or resistor, you should incorporate the R. So we are doing the ideal. Here are the model. You've got V1, then positive input, then you've got R pi, then you have current source here, you have the C of the 1, B of the 1, E of the 1, and then you have RC. We don't use that output. You have a current in here. It is beta times IB1. This is IB1. And then here, open with ideal constant current source. Or else you had to add a resistor from here to the ground. Then it goes to next stage, RC. So we're dealing with the second one. RC, here's the output. This is the collector of the second transistor. Again, current source. This is beta times IB2. R pi, base 2, emitter 2, and emitter 1 are joined to each other. They're connected. Then it goes to V2, going to the ground. So this voltage is V2. Voltage across this one is VBE2. Now we have a signal. VBE2 of that is not equal, it's a signal. Then you have VBE1. Okay? And that's it, it just completes it. And then this is, of course, IB2. IB2. So we've got both change in the input current. They are not equal anymore. This IB is different from the other one because we disturbed it with the values of V1 and V2. Okay, equations. If this current was IO, I named it IO in the handout, then IC quiescent of 1 or 2 is equal to approximately 1/2 of IO, which is I of RE. This is the I of RE, half of that. Then, this is the DC analysis, of course. VE1 of 2, VE1, 2, minus 0.7 volt. Those are DCs. And, of course, VC1, and then GM1, 1 and the 2, which is GM. It's the same thing. It is IC 1 or 2 divided by VT. So they have identical GM, identical R pi's. R pi 1 and the 2, same, and is equal to beta over GM. So same stuff as we had it before. The two transistors will have identical R pi's because the currents are equal. IC1 from the equilibrium, from the DC equilibrium. They are equal. Half milli, and R pi's are therefore the same. AC equations. So in the AC equations, the first thing is the current coming here is IC2 plus IB2, which is equal to 1 plus beta times IB2. this is IC2 going down, combines with this one, that is actually emitter current of one. Next, emitter current of the other one is the same thing. Coming out of here is the sum of IB1 and beta IB1, which is 1 plus beta IB1. The two currents come together, they have no way to escape. See? There's no path here. If there was a resistor, there would be another current in here. I have to write a KCL. But since they are not, you can say 1 plus beta IB2 plus 1 plus beta IB1 is equal to 0. Because this is not 0, these two numbers, they can't be 0. That means IB1 is equal to minus of IB2. That proves the point. When the base current in one increases, the base current in the other decreases by equal and opposite amount. So if you have a 40 microamp coming in, 40 microamp coming here, if that goes to 50, this goes to 30. Base current decreases by equal opposite amount.
That's it. Is that the current equation? It's IB2 plus, and then on the left is that?
This is IC2 plus
IC2.
IB2. Yeah. This is IC2. It's that IC2. That one. So we have that equation. Now there is another equation, which is, we named it equation 7 in the handout. Now there is a KVL. So take the KVL, go from here to here, that's V1. Move from here to here, it's a negative transition. So it is minus VBE1 or R pi times IB1. Remember, R pi times IB is VBE. So minus R pi times IB1. And then you are here, keep coming here, move from here to here. It is IB2 multiplied by R pi. So we get R pi again multiplied by IB2. And then minus V2, which is this one, to ground. So we start from ground, go here, here to here, here to here, here to ground, equal to 0. So when you arrange them, you will have the following. V1 minus V2 is going to be IB1 minus IB2 multiplied by R pi. Okay, this is equation 8. But because IB2 is equal to minus of IB1, this doubles in size. This whole quantity becomes twice of IB1. Twice of IB1. So what do we get? V1 minus V2 over IB1 becomes twice of R pi. And this ratio is called differential input resistance. Differential input resistance. In other words, what we drew like that, gentlemen, like this, it does have this RD. RD to R pi. It has an input impedance of equal to twice of the R pi. Let's make sure, what's the time there? Oh, we passed the time. Is that right?
Yeah.
Big time. Okay, I will continue on Wednesday, right? So let's stop there.